First of all, let me welcome each and every one of you. This is the first Miami Wave Conference organized by a mathematics collaborative group at IMSA. I think it's a great initiative, and we are looking for a very successful week. At the very beginning of IMSA, Simon Donaldson was with us at the opening conference, and so he is sharing with us the opening of this, let's call it a long tradition of Miami Wave Conference, organized by a collaborative group at IMSA in order to celebrate the achievements of science in Latin America. So we will hear more as and see more as the work proceeds, but without any further delays, let me introduce to you the mathematician who turned gauge theory into a music, a friend of mine of many years, Sir Simon. Simon?
Hello. Yep. Right. Thank you for the introduction. Thank you for the invitation to give this talk. Sorry, I'm not there to be with you all in person. So let's just see. So I click on to share screen. Desktop share. I think that's that. Right. I think we're all there. Can you hear me? Is the sound all right? Okay. So we're going to talk about a topic in complex geometry today. Maybe a slightly unusual topic, perhaps. So everything I'm going to say is based on a series of papers jointly with Fabian Lehmann, formerly my colleague in the Simons Center in Stony Brook, now in Humboldt University in Berlin. So two of these papers are on the archive. The other, we hope, will finish in a few days' time. So the basic motivation and idea is to try to generalize the very well-established Torelli Theorem for Calabi-Yau threefolds. That's to say, these are, by Calabi-Yau, I'm just referring to the complex structure, no metrics in the discussion today. So we mean, in this case, a three-dimensional complex manifold with a holomorphic volume form, that's to say, a nowhere-vanishing holomorphic three-form, call it theta. Though being holomorphic in this context means that the form is closed, so it defines a cohomology class or period point, this is more classically, in the three-dimensional cohomology of the manifold with complex coefficients. Then, for safety, I should assume my manifold technically admits what's called the d bar d lemma. But this will be true, for example, if it admits a calorimetric standard theory. So then the statement is that the assignment of this class in the cohomology to the Calabi-Yau structure gives a local embedding of the deformation space, I mean the local moduli space of deformations modulo diffeomorphisms into the three-dimensional cohomology as not an isomorphism, but as a submanifold of the middle dimension, half the dimension, a complex Lagrangian submanifold. On this is a six-dimensional manifold. So on the three-dimensional cohomology, we have a skew-symmetric wedge product form or intersection form. So that's what we mean by a Lagrangian submanifold. So this is what I think would be understood as the standard understanding of the local Torelli theorem for this closed, compact without boundary, Calabi-Yau threefolds. But our work is really based upon a slightly different point of view, perhaps a bit strange to a complex algebraic geometer, a point of view introduced by Hitchin back at the beginning of the century, where we focus on the real part of the holomorphic form. So we'll write our holomorphic form as rho plus I rho tilde for a pair of real three forms. And then Hitchin showed that taking the cohomology class of rho, of the real part of theta in the real cohomology, gives a local identification of the deformation space with a neighborhood in this real cohomology. So it's a slightly different result, but almost equivalent to the previous one. So just to fix ideas, let's think about what the formulae for these forms would be in the model case where our manifold is C3, and we take the holomorphic form, the standard one. Then taking the obvious coordinates, this would be the expression for rho, where this cyclic notation means we sum over cyclic permutations, and this would be the companion form rho tilde. So that's all the well-established situation of a closed manifold. But we want to extend the discussion to manifolds with boundary. So a compact manifold, but with boundary. So the boundary, which we'll call M, is a five-dimensional manifold. And throughout the discussion, we require everything to be smooth up to the boundary. So let's, supposing we have a Calabi-Yau structure on such a Z, and we will restrict attention to the case when the boundary is pseudoconvex, which I'll recall in a moment what that means. So then we can take our form rho 0 and restrict that to the boundary to get a closed real three form on this five manifold. So the statement is that up to a possible obstruction space, we'll call script K, then we have a good analog of we have a straightforward deformation theory. So in the first statement, I'm going to make the assumption that the relative cohomology group is 0. I'll come back to that in a moment. So if that's true, and if this finite dimensional space, that again we're going to define shortly, is 0, then if I have any form on the boundary close to the given one, there's a complex Calabi-Yau structure close to the given one with that boundary value. And this structure is unique up to diffeomorphism, or precisely up to diffeomorphisms close to the identity, where we mean diffeomorphisms which fix the boundary pointwise. So under these assumptions, the assumption on this mysterious space K, the deformations of the complex Calabi-Yau structure are exactly parameterized by the boundary values of the real three form. What the theorem is saying. So just to fill that in, recall the definition of pseudoconvex. if we take a defining function f, so the boundary is given by f equals 0, then we can take I d bar d of f, and the pseudo-convexity is saying this is a positive 1-1 form on what's called the complex tangent space. We take the tangent space of M, intersect it with I times itself. This gives, in this case, a 4-dimensional subspace of the tangent space of M with a complex structure. And so it makes sense to say this is a positive form. Of course, we need to fix whether what the normal direction is. This is the right conventions. So this assumption on the relative cohomology is not really important. It's just we have a slightly more complicated statement if that fails. What we will do for any closed free form on the boundary, we will say an enhancement of that is an equivalence class of extensions over the whole of Z as closed free forms under the relation that two extensions are equivalent if they differ by the derivative of a 2 form which vanishes on the boundary. So any two enhancements differ by an element of this relative cohomology group. In the previous case, of course, this was 0 by hypothesis, so we didn't need to introduce this notion. Then the statement is exactly the same, except that we fix not just the boundary value, but also this enhancement class. We fix this extra bit of information, essentially in this finite-dimensional vector space. So the essential assumption in our theorem is involving this space script K. Now, actually, I don't know any example where this K is not equal to 0. So all examples that we know, this hypothesis is satisfied, and we have a good, it's a straightforward deformation theory. For example, we know it vanishes for when Z is the standard unit ball in C3. By semi-continuity, it vanishes for all nearby points. So for structures close to the standard ball are exactly parameterized by their boundary values. If indeed there are any cases when this space K is non-zero, then there should be a Kuranishi model, a finite-dimensional model, which describes the deformation theory. But that's not something we've strictly worked out yet, mainly because of lack of motivation, because we don't know any examples. So I'm going to talk a bit about the proof of this and some of the ideas that go into it. And for that, we need some background. The first is background in essentially multilinear algebra. There's some special algebra. It happens in 6 real dimensions, which everything I'm going to say here is already contained in the work of Hitchin, these background sections. So what is this algebra? If we have a 6-dimensional real vector space with an orientation, and we have a 3 form on it, then we can use this to map the space V to lambda 5 of its dual by taking the contraction with the 3 form and then wedging with the 3 form to get up to the 5 form. On the hand, as usual, if we have a volume form, then we can identify the lambda, the codimension 1, lambda 5 of V star with the space V by taking the contraction with the volume form. So if we choose a volume form, we get a map from V to V. Then it's a not too difficult exercise to show that whatever row you take, the square of this map is a multiple of the identity. If we changed our volume form by a factor kappa, then we would just change this multiple by kappa squared. So the three cases where C is positive, 0, or negative are well defined, independent of the choice of volume form. The relevant case for us is when C is negative, and then the form is, in literature, it's called a stable form. I'm not really sure that's a particularly ideal terminology, but that's what seemed to be used. So in that case, we can choose our volume form within compatible with the given orientation, so that the C is -1, and so this map defines a complex structure on V. So this is the basic algebraic input, but in this open set of stable three forms, each form defines a complex structure on the vector space. By similar considerations, one shows that in fact there's a companion three form, a rho tilde, so that rho plus I rho tilde has type 3,0 with respect to this complex structure. So on this set of stable three forms, this open set, we have a map, a very nonlinear, complicated to write down in coordinates map from S to itself, which takes the form rho to its companion form, rho tilde. So that's enough algebra. Now turn to geometry on a manifold. We consider a three-form row which is stable at each point. So this thing defines an almost complex structure and a type 3,0 form, rho plus I rho tilde. And the integrability condition for this almost complex structure takes a very simple shape in this setup. It is just that this form is closed. Let's take a moment to see that. So in general, the integrability condition, I'd say the vanishing of the Nirenhaus tensor, is that the exterior derivative has no component mapping the 1,0 forms to the 0,2 forms. If we have an almost complex structure, we can decompose the forms into bitype in the familiar way, and then this is the condition that actually we have a complex structure. Now, given our theta, we can characterize the 1,0 forms by just saying that their wedge product with eta is 0, because that will be a form of type 4,0, which is above the dimension of the manifold, so it has to vanish. So if we take the exterior derivative of this equation, when d theta is 0, we just get that d eta wedge theta is 0, which implies the integrability condition, because if d eta had a component in omega naught 2, that would be when we wedge with theta, that would still be non-zero in omega 3 2. So from this point of view, a complex Calabi-Yau structure is given by a closed stable three form rho. That's a sort of easy thing to write down because stable is an open condition. It's easy to write down closed forms. They're locally the derivative of a two form. But we want these to satisfy a PDE, a nonlinear PDE, but we take f of rho to give us the rho tilde, then that should also be closed. So in our context, we're working within a given enhancement class. So we take some reference point underline rho. We're allowed to vary our three form by the derivative of a two form. So we get this equation for a two form sigma, and our boundary condition is that sigma vanishes or the restriction of sigma to the boundary is 0. So what we're considering is a deformation result for this nonlinear PDE, of course, modulo the action of the diffeomorphisms. So let me tell you now what this space curly K is, the crucial thing appearing in the statement of our theorem. So we have this complicated nonlinear map F on threefolds, but the derivative at our given point rho is a much simpler thing. So this, in fact, is a non-standard complex structure of the threefolds, different from the one induced by the almost complex structure. It's equal to I on the 3, 0, and 2, 1 forms, and minus I on the other forms. So this vector space is, in words, it's just the infinitesimal deformations of the solutions to our problem, modulo infinitesimal diffeomorphism. So the infinitesimal deformations, they're given by the d sigma satisfying the linearized equation, that's dj d of sigma is 0, satisfying the boundary condition. We divide by the deformations coming from diffeomorphisms. Those are given infinitesimally by vector fields, so that there should be a member of symbol here, a typo. So we're taking the vector fields v, which vanish on the boundary, and we take the Lie derivative of rho. So that's what K is. So just to see that the bottom here is indeed a subspace at the top. What is this djd? It's actually something rather familiar. From the definition of J, this vanishes on omega 2, 0 and omega 0, 2, and is essentially d bar d on omega 1, 1. So the linearization of our equation is essentially the d bar d operator on 1, 1 forms. So from the way we've defined it, this space K is clearly relevant to the uniqueness question, because it's given by the infinitesimal deformations modulo diffeomorphism. But it's perhaps slightly surprising that it's also what appears in the obstruction question, the obstruction to deformations. The reason for that is you can see that, well, that ought to be true from a variational formulation, again, due to Hitchin. Any stable form defines a volume element given by rho, wedge, rho tilde, up to a simple factor. And the derivative of this with respect to rho is given by taking the wedge product with the companion form, rho tilde. So Hitchin then considers the total volume as a functional on the closed stable three forms, but in our case, in a given enhancement class. Hitchin, of course, was working on a closed manifold, so this would just be a given cohomology class. So what is the Euler-Lagrange equation for this functional? We consider an infinitesimal variation, and then the variation of the boundary is by this pointwise formula, given by taking the derivative of sigma wedge with rho tilde. But then we can integrate by parts to write that as integral sigma wedge d of rho tilde. And because sigma vanishes on the boundary, there's no boundary term. So the Euler-Lagrange equation is d rho tilde equals 0, exactly the equation of interest to us. In other words, the things we're studying arise as the critical points of a functional, and in that situation, it's always true that because the linearized equation is given by the Hessian of the functional, which is so is therefore self-adjoint. So it's always true that the obstruction problem and the uniqueness problem are essentially the same for any solutions of a variational problem. So I say this suggests, as I just said, is that the linearized operator should be self-adjoint in a suitable sense, and the co-kernel should be identified with the kernel. Of course, this is really suggests because we're not saying at this stage that we've got any good setup in which we can make proper sense of what these operators are. And that's what we'll come to later. So that's sort of set up the background. In this next section, I'm going to talk a bit about the proof. Oh, what do we got? So let's see. Well, part of the motivation for doing all this is that there's an analogous discussion in 7 dimensions for G2 structures, an analogous boundary value problem. So in that case, the boundary value problem ends up being an elliptic boundary value problem when suitably set up, and then the nonlinear deformation theory can be handled by relatively standard techniques, and there are no convexity assumptions on the boundary. I mean, it's not straightforward, perhaps, to set it up as an elliptic problem, but once you do that, you can fit into more or less standard machinery. This Calabi-Yau case in 6 dimensions is more subtle. The boundary conditions don't give an elliptic boundary value problem, so one needs a more sophisticated analysis of sub-elliptic operators, and also rather than the Banach space implicit function theorem, one has to use versions of the Nash-Moser implicit function theorem. But also an interesting aspect is that one has to solve a PDE on the 5-dimensional boundary, as well as PDEs on the 6-dimensional manifold Z. So the main ideas, in fact, already appear in the case when we just consider domains in C3, where we fix the standard threefold on C3. And to avoid discussions of cohomology, let's just consider domains homeomorphic to the ball to slightly simplify things. So the problem is, if we're given a closed threeform on M, can we find an embedding of M in C3 such that we pull back the standard real part of this theta to our given closed form? So we're really interested in this talk in just the deformation theory. So we're supposing we've got a solution. So that's to say we're just considering M as some pseudoconvex submanifold in C3. And then we want to consider the problem of deforming about this given solution. So let's look at the linearized version of that problem. So we're going to consider an infinitesimal variation, d sigma, of our form on our 5-dimensional manifold M. And what we want to do is to find a section V of the tangent bundle of C3 over M, which of course is just C3, if you like, the trivial bundle, but which satisfies this equation that the Lie derivative of V of rho is equal to d of sigma. So precisely we mean that we take the contraction, this Lie derivative, since rho is closed, we take the contraction with V of rho and then take its exterior derivative on our submanifold M. So this is the equation that we would like to understand. So we want to discuss that. So to understand that, we need to say some words about the geometry, the structures we have on the boundary, on this 5-dimensional submanifold of C3. So as we've said, our structure gives us this complex tangent space we call H, the subspace of the tangent bundle of M, which has got a complex structure. And we can always choose a one form so that H is the kernel of the one form. And then our pseudoconvexity condition is that if we take the derivative of this one form, exterior derivative, that restricts to a positive one form on H. So let's fix theta at the moment. Then you easily see that the restrictions of rho and rho tilde to M have the form theta wedge alpha and theta wedge beta, where alpha plus I beta is a form of type 0 on the complex subspace H. In fact, we can normalize the choice of theta in this situation by requiring that theta wedge omega squared is theta wedge alpha squared. And once we've done that, we also have a canonical Rham vector field. So this is a dual to theta. Theta of the Rham field W. Theta of W is 1, and the contraction of omega by W is 0. So we have a direct sum decomposition of the tangent space of M into H and the one-dimensional space spanned by the Rham vector field W. And then we can write our forms on M as split into, roughly speaking, the forms on H plus theta wedge, the forms on H, in an obvious sense. And we have an operator given by the operator induced on these forms on H by the exterior derivative. But of course, this dH squared will not be equal to 0. There'll be various formulae relating the operators we get when we decompose the exterior derivative in this way. So now let's multiply the Rham field W by I to get a field pointing out of our manifold, a normal vector field. And similarly, we can multiply theta by I to get a one form on the tangent space of C3 at that point. So working on C3 at that point, this is the expression for rho. Like this. It involves alpha and theta, where we restrict to the boundary, theta prime to 0, so we just get the alpha term. So with that discussion in place, we can go back to our equation we want to solve. We take our arbitrary form sigma, we want to find a V satisfying this equation. So we can write that as an equation that by the Poincare lemma in the situation, since the cohomology, we're assuming M is diffeomorphic to the sphere, so there's no real cohomology. So we can write this equation as saying that d eta for a one form eta plus this contraction of rho is equal to sigma. If we take d of sigma minus iv of rho, that's 0, so it's equal to d eta for some eta. So we have an equation for a pair consisting of this vector field V and a one form eta on M. Now we can write V as we have a component in the Rham direction. So we have F times W, component in the normal direction, say G times W prime, and a component in the H direction, let's call that psi. Similarly, we can write eta as a form eta H in our space of forms in the H direction, loosely speaking, plus some multiple of theta, say H times theta. So V is given by three functions, f, g, h, and this section of our subbundle H, of the tangent bundle of M. So now, what have we got? We've got, as I said, the various formulae writing how the exterior derivative works with respect to our splitting. If we take d of eta h, that's given by the horizontal component, but then there's another component which, in fact, is the Lie derivative of along the Rham field of eta h, wedged with theta. And then simply d of h times theta, we get h times d theta, that's h times omega, and then we get this other term. And then similarly, when we contract rho with v, using the formula we wrote down, we get a multiple of alpha, multiple of beta, and this term involving the h direction, psi. Similarly, we can write sigma as a sigma h in the h direction plus theta wedge, a one form, lambda. So we put all that together, we've got two equations to solve, written down here. So one is, this is so in the h direction, f alpha plus g beta plus h omega plus the h derivative of eta is equal to sigma, and then this other equation written down there. So like we said, the form omega defines a positive 1,1 form on H, so it defines a metric. So H has got four real dimensions, and also a natural orientation. It's got a complex structure. Then, it'd be familiar to the people that this triple of forms, alpha, beta, and omega, give a basis for the self-dual forms on H. The anti-self-dual forms can be identified with the primitive 1,1 forms, in this case, just the kernel of the contract of the map where we wedge with omega from 1,1 forms to 4 forms. Now we can also decompose further our dh into d plus h and d minus h components. So that should be a plus or minus, I think. So this is just like what one in four-dimensional Riemannian geometry one is very familiar with doing. We have d plus and d minus operators, components of the exterior derivative in the using the decomposition of the two forms. Similarly, we can decompose sigma, and then the first equation from the previous slide has got two components, the components in the self-dual and anti-self-dual forms. And they're what's written down here. So that's now finished our writing out the equations explicitly. Now we can go on to see what's required to solve them. Supposing we can find eta h satisfying this equation. So this only involves eta h, just if we can solve that. Then these are self-dual forms, but alpha, beta, and omega give a basis for the self-dual forms. So we can find f, g, and h solving this equation. Then if we go back to equation 2, now everything has been defined except for this I psi of alpha. It's the contraction of by psi of alpha. But since alpha is a non-degenerate two-form, the contraction of alpha gives an isomorphism from vectors to from H to its dual. So there's a unique way to solve this equation using psi. So the conclusion is that if we can solve this first equation, then we can solve all the other equations. The first equation only involving this eta h, this section of the dual of h. And this, so remember, sigma minus h is an arbitrary section of the anti-self dual forms on h. So we see that the essential thing is this operator d minus h, mapping omega 1h to omega minus h. If this is surjective, then we can solve the linearized deformation problem, which in turn makes us optimistic that we could solve the nonlinear problem. So the main thing we need to do really is to understand the analytical properties of this operator. Now this couldn't be an elliptic operator because essentially it's only differentiating in the h direction. It's not involving the first order operator. It's not involving any differentiation in the normal direction. So it clearly violates the condition for ellipticity. But we can define a Laplace type operator in the familiar way using d minus and its formal adjoint. And this has certainly the image of this is no larger than the image of d minus. So if this thing is surjective, then d minus is surjective. So the key point now is that there's a version of a Weizenbach formula in this situation. There's a natural covariant derivative, actually it doesn't really matter how you choose this. And then if we compare our delta minus with the rough Laplacian, we only get an algebraic term, a zeroth order term coming in. Then this kind of rough Laplacian, by a part of, I guess, fairly standard sub-elliptic theory, it's not elliptic, but it satisfies an estimate a bit worse than the estimate you have for an elliptic operator. But the L2k norm of any S is controlled by the L2k minus 1 norm of this thing. So if you had an elliptic in the elliptic theory, we would put k minus 2 here, plus a low order term. In the sub-elliptic case, we only gain one derivative rather than two. But anyway, that's enough, because since this is a zeroth order operator, then we get a similar estimate for delta minus. So that implies that the image of delta minus is closed and of finite codimension. So it's something we can work with easily analytically. Where do we go? So this Weizenbach formula, it depends upon the special feature of the situation. It's special to omega minus. We could write down Laplacians on omega plus or on omega 1, for example, in our case. But then we would get another term involving the derivative in the normal direction. The first derivative in the normal direction. So that would prevent us doing the same thing. And in fact, there we would encounter infinite dimensional spaces when we worked on these in this other situation. So the difference comes down to the fact that taking the wedge product with omega, which is the derivative of the contact form, vanishes on omega minus, but not on these other spaces. So now we define our space curly H to be the kernel of the adjoint operator to D minus. So it's a finite dimensional vector space, and in fact we can identify it with the kernel of dh mapping the omega minus h to the omega 3. And then, given the foundational facts mentioned above, it follows that the image of d minus h is the orthogonal complement of this finite dimensional space, stripped h. So, of course, if stripped h is 0, then d minus is surjective, so we can indeed solve the linearized deformation problems. This finite dimensional space curly h arises as the obstruction to solving the linearized version of our problem. Let's just mention we can extend the definition of this vector space H, which we've done in this special situation so far. The definition extends to general pseudoconvex CR manifolds in any dimension with the form 4k plus 1. Let's just say this briefly. So initially, if we choose a contact 1 form, then we can let what's called LKK be the space of 2k plus 1 forms on our manifold of the form sigma wedge theta, where sigma is a KK form on H. And then, well, it's easy to see this is actually, this space of forms LKK is independent of the choice of theta. It's something that just depends upon the CR structure. Then we simply take the closed forms in LKK, the kernel of D intersect LK. Well, in fact, that's the complexified version of our space H. If we took sigma to be a real form in a suitable sense, we would get our space H, the real vector space. So the point here is that the condition, again, the exterior derivative has a component given by wedge with omega. So this condition that the form is closed is saying both that the horizontal derivative dh of sigma is 0 and that sigma wedge omega is 0, which in another point of view is saying that sigma is actually a primitive KK form in the language of Kähler geometry. So now we'll be rather vague from now on. So if we go back to our theorem 1, the analysis combines the above discussion on the boundary, solving this equation on the boundary, with solving equations in the interior using considerations from Hodge theory for manifolds with boundary and variants of that, and also the D-bar-Neumann theory. So one gets exact sequences relating the space K that we've defined with the space H, defined just by the boundary, and various other more standard cohomology groups involving the geometry and topology of the situation. But in the case when Z is a Stein manifold, so all the sheaf cohomology groups of Z vanish, then of holomorphic, all the holomorphic cohomology groups, you might say, above dimension 0 vanish, then it turns out that this space K is just the kernel of a map from curly H to the three-dimensional relative cohomology of Z with M. So this involves Nash-Moser theory, as we mentioned, and also sub-elliptic estimates. In a similar fashion, much of it to work. There's a large literature on deformations of complex manifolds with boundary, but when you're thinking of in terms of deforming the CR structure on the boundary, rather than deforming the forms on the boundary, as we are considering here. So some examples of what we know. We know in a sense very rather little about what this space with script H is rather mysterious. It doesn't seem to, well, there doesn't seem to be any literature which would tell us much about it. But if we had a Sasaki-Einstein manifold, M, for example, the standard 5 sphere, then one can prove that H is 0. Another interesting example is if we take M to be the product of the 2 sphere with the 3 torus, which we can think of as the boundary of the 3 ball times the 3 torus, regarded as a subset of the quotient of C3 by Z3, or I times Z3. If we take C3 over I times Z3, we get R3 times T3, and we're just taking the ball in R3. Then that's more interesting. Then the space H is one-dimensional, but this map pi is non-zero, mapping into the relative cohomology. So that implies that in fact K is 0. So in both these cases, we do have a simple deformation theory in our problem for when we deform. We want to deform the complex structure about this kind of standard example. So I have a section 3, but my time is almost up. I think I started a bit late. Can I?
Yeah.
Can I go on for 5 minutes? Can I go on 5 minutes?
Yes.
Okay. So yeah, so I was going to say 2 things. I'll just say one of them. Let's say more about this case when M is S2 times T3. But let's restrict attention to forms of this shape. So we'll take y1, y2, y3 to be coordinates in the T3 direction. And let's take a triple of 2 forms, omega 1, omega 2, omega 3, on the 2 sphere. So these are invariant under translation in the T3 direction. So we go from a problem in 5 dimensions and 6 dimensions to a problem in 2 dimensions and 3 dimensions. Then this is really not at all obvious, but it's an elementary, in a sense, exercise to see. The problem of the problem of finding an embedding of an embedding of the kind we're considering, which pulls back the standard form to this one, is equivalent to a very famous problem in differential geometry and analysis, what's called the Minkowski problem for convex surfaces in R3. So in a Euclidean formulation, just to say what this, remind you what this Minkowski problem is, it says if we're given some positive function kappa on the 2 sphere, can we find a convex surface in R3 so that the Gauss curvature at any point on the surface is equal to the value of our function kappa on the normal direction to that point? So in this case, in this dimensionally reduced case, we can go beyond small deformations to show we can consider large deformations. So in general, we would like ideally to do something similar in the general situation for 5 manifolds. If we imagine starting with our standard structure on the 5-dimensional sphere, for example, we keep on deforming the closed 3 form within the 3 forms on the 5 sphere. Can we carry on deforming the Calabi-Yau structure on the ball to match, or do we meet some kind of do we develop some kind of singularities or something as we attempt to do that. So this is probably a very difficult problem in general, but there are interesting things one can do and think about in that direction. I had a final section I was going to say a little bit about that, but I'm out of time. Everything I was going to say in the last bit is contained in the second paper of the three that I mentioned on the first slide. So I'll finish now. Thank you for your attention.
Thank you, Sam.